This problem, for example, they say here a built-up section is fabricated from 16 millimeter plate. Determines the resisting moment about x and y axis. So what we can do here about x axis, for example, we need to calculate the resisting moment. To calculate the resisting moment, we need to know whether this section is class 2 or 3 or 4. Because if it is class 2, the resisting moment will be phi m sub p. If it is class 3, it will be phi m y, and so on. So we need to know the classification of the section first. So we have to identify the direction of the moment. So here I will assume that the moment along x-axis will compress the top part and elongate the bottom part. So in this case, based on what we see, you have that flange free from one side and supported at the well. So I consider B sub EL as 50 and the thickness of the flange T as 16. And I check it with the classification of class 2 in this case. And then class 3. Then between that well and that well, that top flange is supported from two sides. So I calculate B sub EL over T, which is going to be, this is 50 and this is 50, and the thickness of the blade is 16. You subtract it from 400, you can get that length. Divide over T, then check it with the limit for class 2 and 3 for a plate supported from two sides, which is the case of HSS. Then take the width h over w and make a check to see whether it's class 2, 3, or 4. So this is what we did here first. I divide the section into three plates. Plate 1 that is free from one side and supported at the well. So I calculated B sub EL over T as 50 over 16. I check it with the limit for class 2 for a flange supported from one side, 170 over root of 4. I found that B sub EL is then the limit, less than the limit, so my section is class 2 for plate number 1. But what about plate number 2? Plate number 2 has B sub EL over T equal 16. But this plate supported from two sides, based on what we mentioned here. Elements supported along two edges, the same as the flange of box beam. The limitation for class 2 is 525 or square root of y. For class 3, 670 or square root of y. So let's take that limit. So this is what we did here. The limit for class 2 is 525 over square root of y. I got it 30. Since h over w, since b sub el over t is less than the limit for class 2, so that flange here, plate, meets the criteria for class 2. So it looks like both plates meet the criteria for class 2. But what about the web? The web has h over w, so we take the height of the web 400 over w, which is 16. I got here 25. But the limit for class 2 for the web is 1700 over root of y. Since h over w is less than the limit for class 2, the web also is class 2. So it looks like the three plates in compression meets the criteria for class 2. So basically my section is class 2. But before we proceed, from where I got the 1700 over root of y as the limit for class 2 for the web, I go to that table, table 2. You find here that for class 2 for the web of I beam, I use h over w 1700 over root of y for class 2, and for class 3 it's 1900 over root of y. Since the whole section is class 2, the stress distribution should meet the criteria for class 2. How? You have rectangular stress broken compression and other one in tension, as you see. So what is the corresponding moment here? Someone would say, as I did here, I said that that stress distribution will act on these three plates here, creating a force in compression C, SC. And I have similar one in tension. So if I know the distance between the two forces, which is A, I can say that C times A will be the moment. So I can say here C is Fy times that area of compression. Times A will give me the moment. But what is A here? Someone would say, I can take this plate and this plate and that plate, take the moment of each area about the neutral axis, This will equal the whole area times A over 2. So we determine its location. And in this case, we can get the resisting moment as phi C times A. Phi is with 9 and A we got it. And C is Fy times that area, which is A sub C is the complete area. That's the area and compression. I did it here by determining the centroid of that part in compression. But you can do it the same as we did in the example we covered last time. A section like this, and I do determine the resisting moment. So I draw the rectangular reciprocal compression and tension, and I calculated the force in each segment. So in that top flange, the force will be C1 as the area of the flange times Fy, and the force in the web here will be C2 as the area of the web times the force of the stress Fy, and you can do it for T1 and T2. Then take the moment of C1, C2, T1, and T2 about the neutral axis. This will be directly the plastic moment. So this is actually other easy way to do it here. So I solved some problems this way by calculating the centroid of that area through distance A here. Or later on I will show you that I take the moment of forces the same as I mentioned in the example last time. But what about if the section is not symmetrical? They tell you a T section shown is fabricated from 350W steel plates welded together. Assume the section can develop full plastic bending. Can develop full plastic bending means that it's a class 2 section. So you don't need to determine the classification of the section. So basically the stress distribution should be rectangular in compression and tension with intensity Fy. But the problem here is that to calculate the resisting moment about x-axis, I need to determine the location of neutral axis, the same as what you did before. Assume that the depth of the neutral axis from the bottom of the section is y. Then equate the area and compression with the area and tension. So the area and tension is this one, 20 times y. 20 times y. But the area and tension should be, the area and compression should be 200 times 20, which is what we see here, plus that area, which is 200 minus y, times the thickness of the plate, which is 20. By solving that equation, I got y as 200. But the depth of the web is 200 here. This means that the neutral axis will be exactly at the bottom of the flange, something like this. So if the neutral axis at the bottom of the flange, whatever over the neutral axis will be in compression, whatever under the neutral axis will be in tension. So basically, what is the corresponding resisting moment? I can say concentrate the stress in a force in the top flange, so it will be C. Concentrate the bottom stress and tension in the bottom flange or the web here to be T, and the moment will be C times A, or you can take the moment of C and T about the neutral axis. Yeah, you remember when we proved that Zx equal A sub C times A? Yeah, or we can calculate it by taking the moment of forces here. But here we calculate Zx as cross-section area times A. And A here is known because you know the centroid of that web, which is half the height. The centroid of this one, which is half the height of the flange. So in this case, A will be half the height of the web plus half the height of the flange. And the area and compression will be 200 times 20 for the web, for the flange, or the web because they are the same, times Fy, you will get that resisting moment. So if you don't want to do it this way using Zx equals so, you can say C equal the stress Fy times phi times that area. And T is the same. Then take the moment of C and T about the neutral axis. The same as what we did in that example. Take moment of forces about the neutral axis. It will give you the same value. But what about that case here? You remember when I told you if the web is class 4, but the flange can be class 2 or 3. So basically calculate the resisting moment as it is class 2 or 3 here, then multiply by reduction factor. Also, if the flange doesn't meet the criteria for class 3, so it is class 4. If the flange is supported from two sides, reduce its width to be 600 T over 45. If the flange is free from one side and supported at the one side, here you take 200 T over 35. Did we find this in the exam? So they say here, the section shown is fabricated from steel plates 16 millimeter each. Determine the amount of resistance about XBB. Make it AA first. AA. XAA. So let's assume that the amount will cause compression on that side and tension on that side. This is what we did here. So if it causes compression here, so this will be plate number 1 for the flange, and this will be the width. So for plate number 1 and compression here. So basically, it's a plate that is free from one side and connected to a well. So take B sub EL as 200 and T as 16. So B sub EL over T equal 12.7. And the classification for class 3 here is 200 over 34. So it looks like your B sub EL over T is more than the limit of class 3. So it should be class 4. So how can we deal with that flange if it's class 4? We say that shrink it to make it class 3. So how? Okay, what we do here, we reduce its width to be, you see here, we reduce its width to be 200 T or 35, so it is 185. So 185 rather than using it 200. But what about the width here? Does it meet the criteria for class 2, 3, or 4? Yes, we calculated H over W as 23, and the limit for class 3 is 1900 or 35, so it meets the criteria for class 3. So your problem here isn't the flange. It doesn't meet the criteria for class 3, so it is class 4. So what is the corresponding resisting moment here? You need to calculate an equivalent elastic section modulus, SE. How? You take the section again with a reduced flange width in the compression side, because we assume that the moment acts this way. In the tension side, you keep the flange as it is, because it doesn't have any problem with buckling. So the problem here in that case is that originally the member was symmetrical about AA when you calculate the amount of inertia or so. Now we reduce that width a little bit. So in this case, that neutral axe will move a little bit to that side. So I have to calculate it. So how can we calculate the location of the neutral axe here? I assume the depth of the section of the neutral axe as y bottom, y left from the left of the section. How can I get y left here? I say, take the moment of each area. Here's these three areas about the side of the section. This will equal the whole area times y left. So this is what we did. I got y left. So you can enjoy calculating the amount of inertia of each one locally, then multiply by the area times the distance between the two centroids square. Everything the same as we did last time. Then we calculate the elastic section modulus as Iy over the greater of y left and y right. So y left here will be greater anyway. So we calculate the elastic section modulus, then multiply by phi fy, you can get the resistance. So this is just an example of having a section that is class 4. And we need to reduce it.